Hello, my name is Brian Lee. I am a distance learning student in my first semester at North Carolina State University and am enrolled in ECE 535. After consulting with Dr. Buckner, I elected to build a simple magnetohydrodynamic drive for my experimental demonstration project. A magnetohydrodynamic drive is an engine with no moving parts that creates thrust by using the Lorentz force to accelerate a charged fluid within an electromagnetic field. Hendrik Lorentz was able to determine the total force exerted on a moving charge in the presence of both electric and magnetic fields, and went on to determine the force on a current carrying conductor caused by an external magnetic field. In order for a magnetohydrodynamic drive to work, electrical charges must flow through a fluid. The addition of mediums known as electrolytes make this possible. An electrolytic solution is created when a salt is placed into the water and the components dissociate. Sodium chloride is used as an example here. When electrodes are placed in an electrolyte and a voltage is applied, the electrolyte will conduct electricity. Lone electrons normally cannot pass through the electrolyte. Instead, a chemical reaction occurs at the cathode, providing electrons to the electrolyte, and another reaction occurs at the anode, consuming electrons from the electrolyte. The ions in the electrolyte neutralize these charges, enabling the electrons to keep flowing and the reactions to continue. The resistance of the electrolyte to the flow of electricity can be determined. It is proportional to the distance between the cathode and anode, and is inversely proportional to the cross-sectional area of the cathode or anode. I purchased a small plastic reservoir to hold the electrolyte. The reservoir measures 28 centimeters long by 15 centimeters wide by 19 centimeters tall. I chose aluminum to fashion the flat plates I would need to create a cathode and an anode because it was readily available at Lowe's Hardware. I created two strips, each measuring 4 centimeters in height by 19 centimeters in length. I purchased a set of ceramic magnets from Amazon. These are also known as ferrite magnets and are composed of strontium carbonate and iron oxide. The manufacturer states that these magnets have a residual magnetism of 3,850 Gauss or 0.385 Tesla. Individual magnets measure 1 7/8 inch length, 7/8 inches in width, and 3/8 inches in height. I made use of a universal selectable voltage AC to DC adapter from Radio Shack. The device is capable of providing 3, 6, 9, 12, and 15 volts DC. Finally, I built two small stands to keep the electrodes in a fixed position during the experiment. The parts were assembled and used to run a series of controlled experiments to monitor the effects of changes in salt concentration, magnetic field intensity, and applied voltage on the magnetic force produced. The time for a marker added to the solution to travel the length of the plates, 19 centimeters, was measured. I designed the experiment so I could adjust the distance between the electrodes, as the resistance in the solution is proportional to the distance between the plates. If I assume the resistance in the leads from the voltage source are negligible, the current flowing through the solution should be equal to the applied voltage divided by the resistance. For a given voltage and fixed distance, the current will be a function of concentration. And since current is directly proportional to magnetic force will be a function of concentration when all other variables are held constant. For a given distance between electrodes and given concentration of sodium chloride, the voltage is directly proportional to the current, and the increase in current will lead to an increase in magnetic force. I calculated values for current as a function of salt concentration, distance between electrodes, and applied voltage. Here is an example showing current as a function of salt concentration for distances between 4 and 10 centimeters and an applied voltage of 15 volts DC. I estimated values for magnetic flux density as a function of block dimensions and distance from the face of the magnet. If all other variables are held constant, the magnetic force that is developed will be directly proportional to the magnetic flux density. I estimated values for magnetic force for a given concentration, distance between electrodes, voltage, and magnetic flux density. Here's an example showing magnetic flux in millinewtons as a function of voltages between 3 and 15 volts DC and an average flux density of 0.13078 Teslas. According to Newton's second law, the square of the time it takes a mass to travel a fixed distance is inversely proportional to the applied force. This principle allows me to make predictions about the changes I should see in elapsed time as I manipulate the aforementioned variables. The results were mixed. Changes in the square of the elapsed times were in the direction I expected, but the values were much larger than anticipated. Results may have improved had the method of timekeeping been more precise. I will close by showing a brief video where I employed the test equipment to measure the elapsed time for a given set of conditions. I hope you enjoyed this presentation, and I thank you for your time and attention.
I'm gonna just start. Ready? Go. See it? Perfect.